We will introduce our proposed method, which is deep burst multiscale superresolution using Fourier space with optical flow, called BurstM. The source code has been released at the GitHub link below. Image super resolution aims to restore high-resolution images from low-resolution images. Burst super resolution utilize multiple frames of low resolution. To perform burst super resolution, precise alignment is required due to misalignment between frames. Furthermore, advanced merging and upscaling performance are also required to exclude noises. Recent burst super resolution methods use deformable convolution network as an alignment module. Deformable convolution network is a good method, but it has some limitations. First, the general usage of deformable convolution network involves using a single convolution to generate convolutional offsets, but a single convolution cannot cover global alignment effectively. Second, deformable convolution network requires a predefined number of kernels regardless of the correlation. If deformable convolution network can't find correlated information, deformable convolution network takes outer pixel information, and it leads blur and incorrect images. In addition, existing methods use pixel shuffle as their upscaling module. While pixel shuffle can reduce computational complexity, it restricts the flexibility of scale factors. The overall pipeline of BurstM is as below. The network aligns features using only optical flow without deformable convolution network. In addition, we perform precise alignment and upscale on Fourier space. By adopting implicit neural representation, BurstM has capability of multiscale superresolution, which is different with existing methods. Finally, our approach did not use transformers for feature extraction but applied CNNs, and by adopting implicit neural representation, we were able to achieve efficient computational costs. We prepared residual map to analysis alignment performance. In methods using deformable convolution network, misalignments are prominently visible, leading to blurred images. Additionally, since deformable convolution network requires using all predefined kernels, it can result in boundary artifacts when it fails to capture correlations, as it takes information from the boundaries. However, BurstM use optical flow only. Thus, BurstM takes correlated pixel only due to one-to-one correlation. And the result shows accurate alignment performance without the boundary artifacts. By adapting implicit neural representation, BurstM can perform superresolution at arbitrary scales directly without any downsampling. It is also capable of handling arbitrary scales that were not seen during training. Although we only trained BurstM for scales of x2, x3, and x4, as shown below, it performs well for both in-scale and out-of-scale scenarios. This table shows the quantitative comparison on both synthetic burst and BurstSR. For synthetic burst, we compared the various scales and we compared x4 scales only for BurstSR. BurstM can estimate various scale directly, but the others are by cubic downsampling result after x4 scale super resolution. As highlighted red and blue colors, BurstM shows best performance except for synthetic burst x4 scale. If we consider the number of model parameters, BurstM indicates best performance with reasonable parameters. In addition, less scale factor of BurstM shows higher PSNR in synthetic burst. It is natural. However, the other methods are lower PSNR due to missing information during downsampling. The qualitative comparison of BurstSR scale 4 with latest methods such as BAPNet, BurstorMer, BSRT large. BSRT large and BurstM shows clearer estimation result than BAPNet and BurstorMer. Moreover, as you can see red arrows, BSRT large shows boundary line artifact on the edge of frames. Therefore, BurstM has best PSNR and SSIM than the others. For synthetic burst, we can use the quantitative metrics or specific methods. Below images are residual map with ground truth. The bright color means high difference with ground truth. Looking at the red arrow area, the existing methods lost the information during bicubic downsampling, but BurstM keeps stable representation regardless of scale factors. Recent methods adapt transformer due to higher performance. Transformer-based models have small parameters, but they have heavy computational cost. Thus, transformer-based models shows long inference time. However, BurstM is CNN-based model and estimates on Fourier space. Thus, BurstM achieves fastest inference time and high performance together. The conclusion is as below. Our network conducts precise alignment using optical flow without deformable convolution network on the Fourier space. We solve the fixed scale issue in MFSR and demonstrate our flexible networks of multi-scale SR. Extensive experiments demonstrate that our approach outperforms existing approaches in both image quality and computational efficiency.